So let me get that question on the video because that's a great question. So the first question that I really like there is, where does the speed come into play? So you can imagine a bearing, for example, a ball bearing. That ball bearing is contacting at a point, right? As it's rotating, that point is no longer in the contact anymore. So if I'm going to use a particular ball bearing assembly for 30 years, say, or 15 years, then where where the speed comes into play for the balls rotating comes into play is a number of cycles, because that point A is rotating, right? But the higher the speed is, then the higher the wear is over time, because I have more speed. So that point A is touching the raceway many more times as if it was going slower. So the extreme case is if the ball bearing on a raceway is just there statically, then there's no cycles to failure. So there's no fatigue issues. And that's 0 RPM. But now I go to 5,000 RPM, revolutions per minute. And so now that ball bearing at a particular point in the contact zone, that point at that location is going to see that again at some point, but it's going to see it many more times over the life of the bearing. And that's where fatigue comes into play. Great. Moving on then, we'll step into some examples, very easy formulas to use. So I don't want to really spend too much time into this, but let's compare the maximum volumetric stress for a spherical case and a cylindrical case. So I want to look at two cases, and I want to do as a function of contact force. I'll study two cases. All the cases are going to use steel as a modulus. And the sphere is going to be about 10 millimeter sphere on a flat plate, and the cylinder is going to be 10 millimeter by 0.5 millimeter cylinder. Diameter is 10 millimeter. So we're going to make that up, some observations. That's the question being asked. So when I look at that problem, I'm going to go straight to the plots, use the formulas I gave you already, and I invite you to replicate this in the comfort of your computer. In the y-axis, what I'm showing is the volumetric stress in the maximum value. In the x-axis, what I'm showing is the contact force. What you see here really quickly is that the sphere, for a given contact force, right, because I'll bring the two pieces together with a force F. For the same contact force, you can see that it's almost double. The sphere produces more stress than a cylinder by a factor 2.5 or so. And you can see that all along. The second observation you have here is that as you increase the contact force, the behavior is not linear, meaning it doesn't follow a slope here. It kind of tapers off at some point. And that makes sense because the contact surface is developing as you apply the load, and it's developing more and more and more to the point that things are more uniform across that contact area. And so that volumetric stress also tapers off, as you can see here. It continues to increase, no question, but not like it was at the beginning. At the beginning, it was way faster. So just wanted to point that as an example. And this is a good example because that's something you can program in Excel very quickly to see if you can get the same plot I have, either Excel or MATLAB. And I invite you to do that as a practice on how to use software for solving different problems. So then you're not surprised later on. The next example, and I jumped to example 4 from number 1, because to me, these are like 3 examples in one. You're doing the contact sphere, you're doing the cylinder on a flat plate, and then you're comparing them. I mean, that'll be a good problem, right? Because you're doing like 3 or 4 problems in one. The next problem is looking at a 50 millimeter diameter ball, which is pressed against a spherical seat of diameter 75 millimeter, and then it has a force applied of 500 newtons. And the materials involved here is 200 gigapascals for the steel, and the Poisson ratio is 0.3. We want to calculate the radius of the contact area, number 1. We want to calculate the contact pressure, number 2. And then we want to calculate the relative deflection of the centers of the ball and the seat. On the bottom right, what I show is the situation of a ball joint. And that ball joint is an example where you could encounter this. You can encounter this in those kind of problems. What I like doing when I solve a problem is to write down all the variables that are given to me so I have a clear understanding of what was provided to me. What's provided to me in this problem as step number one, I'm given the diameters of the balls. I'm given the contact force, the force applied, and then I'm given the modulus and the Poisson ratio. And then I want to find the area of contact, the radius of the area of contact, and then I want to solve for the maximum pressure. I also want to solve for the deflection D. So that's at the bottom right. So that's actually very useful because you can then um, kind of understand the variables are provided to you. Again, this is two spheres. One of them is inverted, obviously, because it's sitting on a ball joint. So one of the things you can do is to look at the geometry. The geometry is provided here. Apply a force here to this sphere. That's the problem I have. And you can then put this in Excel, right? So I'm giving D1, D2, all these formulas. So put it all here very clearly. And you have that. Put the units here so everything's clear. And then you put the units here. And I put everything in consistent units. So it's in meters, pascals, and newtons. So again, when you go to industry and you're given a problem, nobody's going to tell you to make sure your units are consistent. That's something you have to be worried about. Not your manager's not going to be asking, hey, make sure you're using consistent units. No, that's something you need to start with right away. And then you then determine what are the equations that are the most relevant to the problem. And the equations I already gave them to you earlier. You look through your handbook. Maybe you don't have a handbook. Maybe my course notes are your handbook. Whatever it is, you pull it up and say, okay, these are the equations. And by the way, do not use my notes as the handbook because as you've seen, there have been some amount of errors. You want to use something like my book, right? That has been proofread by industry experts. You can use the book for this course, also has been approved, although I believe there's an error there with a sign convention I discussed before. Again, any book you use, you want to make sure it's correct, obviously. And Wikipedia may not be the best source. But here you have the formulas provided to you, and all you have to do is plug it in. And then you're ready to go by calculating the output, by using these formulas in Excel, and then here in the notes, I wrote the formulas so you can see what they are.